The loss of the aircraft forced Juan de la Cierva to search for a completely new way to fly. His main goal was to eliminate the danger of an aircraft losing speed. To achieve this, he decided to abandon the traditional airplane wing and began looking for another solution. At first, he turned his attention to the ornithopter and the heliopter. The principles of their flight had been known since ancient times, but in practice, no one had ever managed to build a properly flying machine, although there had been many attempts. An ornithopter is a flying machine heavier than air that rises into the sky thanks to wings that flap. Throughout history, humans dreamed of becoming like a bird and soaring into the sky. But no one succeeded except for the heroes of legend, Daedalus and Icarus. The idea of the heliopter is based on a different principle. Lifting force is created by a propeller rotating on a vertical axis, powered by an engine. Many people worked on this idea, but a truly functional machine was still very far away. The first heliopter to rise into the air with a person on board was built by the Breguet brothers and Professor Richer. This happened on September 29, 1907, in the city of Douai. However, the ascent was conditional. 4 people with poles held the machine steady. The first free ascent was made by Paul Cornu, who on November 13th of the same year rose a few feet into the air in his twin-rotor machine without any support from the ground. After the First World War, work on heliopters continued in almost all industrially developed countries. Here we can mention the names of Pesquera from Spain, Bodazat and Bleecker from the United States, Baumhauer from Holland, Dascanio from Italy, Invention and Breguet from France, and Fock and Flettner from Germany. The results of early heliopter research in one country were usually not well known in others, and often new ideas in this field developed in parallel and independently of one another. In Russia, several interesting projects were also carried out. As early as the beginning of 1907, military engineer Konstantin Antonovich Antonov began developing a heliopter project, which was built 3 years later. 2 propeller wheels, the lifting rotors, were made of separate triangular aluminum blade plates. The blades could rotate around their longitudinal axes. A small propeller, according to the author's idea, was supposed to create horizontal thrust. The machine was powered by an engine of 35 horsepower. The tests did not produce positive results. The heliopter built in 1909 by Igor Ivanovich Sikorsky, a student of the Kyiv Polytechnic Institute, had 2 coaxial 2-bladed rotors driven by an engine of 25 horsepower, although the engine was very worn. By the spring of 1910, Sikorsky had built a second heliopter. It had 2 3-bladed rotors and a new engine with a power of 25 horsepower. The machine weighed about 400 pounds. The designer did not complete his work, redirecting his efforts at that time toward building airplanes. In 1911, Boris Nikolaevich Yuriev, a student of the Moscow Technical School who would later become an academician, created a project for an unusual helicopter. At the center of the machine stood a gnome engine with a power of 70 horsepower. The helicopter had a main lifting rotor and a tail rotor. To control the flight, Yuriev invented a special mechanism, the swash plate. This device allowed the direction of the lifting rotor's thrust to be changed and therefore the direction of the helicopter's flight itself. At the end of 1911, Yuriev developed a second version, a helicopter with a single rotor. It was built only at the beginning of 1912. The diameter of the 2-bladed lifting rotor was about 26 feet. To prevent the machine from spinning in the air due to the rotation of the main rotor, a tail rotor was installed at the end of the tail boom. Both rotors were driven by an engine of 32 horsepower through a transmission system. In the spring of 1911, this helicopter was exhibited at the Second International Aeronautical Exhibition in Moscow. The designer received a gold medal for fundamentally new elements of the helicopter's construction. Although this aircraft never managed to lift off the ground for several reasons, its configuration and its swash plate give every right to consider it the forefather of modern helicopters. In the early 1920s, helicopters rose only to a height of a few feet and flew a distance of a few hundred feet. The world record for straight-line flight distance was set by the Emixon helicopter on April 17, 1924. Only 2,414 feet. Why was progress so slow? The machines vibrated heavily, handled poorly, were unstable in flight, and most importantly, could not glide when the engine stopped. Designers persistently searched for solutions to these problems, trying to eliminate the shortcomings, but so far no one could propose anything revolutionary. Parallel to the attempts to create a real flying helicopter, scientific work was being conducted, including in aerodynamic institutes. In 1910, Nikolai Yegorovich Zhukovsky identified three of the most important of them: the Roman Institute, the Tesseum Institute in the United States, and the Aerodynamic Institute in Kuchino. The latter was founded in 1904 and became the first institution of its kind in Russia. The creation of this institute and the initial period of its work were closely connected with the name of Nikolai Yegorovich Zhukovsky. The scientific results obtained at the Kuchino Institute and published in its bulletins were highly appreciated not only in Russia. Thanks to French publications, they became known abroad as well. Now let us make a small digression that may have direct relevance to the invention of de la Cierva. Here is what the founder and director of the Kuchino Institute, Dmitry Pavlovich Ryabushinsky, wrote in a brochure dedicated to the Institute's 10th anniversary. The main results that I obtained in the Aerodynamic Institute are as follows. I systematically studied propellers and discovered the general laws governing the operation of this remarkable mechanism. In these studies, I did not limit myself to examining propellers alone, but also covered the area of windmills and the field where propellers throw liquid in the direction of motion. This gave me the opportunity to obtain a very complete picture of the phenomenon. I expressed the results through several simple formulas which are now used in practice. I indicated the foundations of the vortex theory of the propeller and a graphical method with special coordinates. I also studied both experimentally and theoretically propellers working in place and under a side wind. I discovered and explained several interesting phenomena of great theoretical interest, such as the self-rotation of thin plates. Let us not criticize the author's style or the fact that he attributes all the Institute's work to himself. Let us simply note an important fact. The results of the studies on air propellers and the self-rotation of a symmetrical plate were published in 1909 in the Bulletin of the Kuchino Institute in the French language. De la Cierva knew French well and at that time read everything about aviation that he could get his hands on. It is quite possible that he may have come across this bulletin, and if so, then this idea could have fallen on prepared soil and caused a flash of insight. Having studied all the experience humanity had accumulated in creating ornithopters and helicopters, de la Cierva realized that these machines were too complex from both mechanical and aerodynamic points of view. He concluded that the problem of safety could be significantly improved if one created a system of wings that would move relative to the aircraft while remaining structurally connected to it, and would maintain this movement without using an engine. According to some of de la Cierva's biographers, including José Varleta, the initial idea came from a children's toy, the so-called Chinese top. Observing the smooth descent of the toy, de la Cierva realized that there are modes in which a rotor can rotate on its own. On practice, however, the problem was that the lifting force of each wing had to make it move relative to the aircraft at the same time. La Cierva considered different options and settled on a system of wings that rotate around an almost vertical axis. He called this system the rotor. The rotor performed the same functions as the lifting rotor of a helicopter, but unlike a helicopter, it was not powered by an engine. It rotated freely under the force of the incoming airflow. This phenomenon received the name autorotation. To maintain autorotation, the airflow had to approach the disc with a certain upward component, meaning the disc always had to maintain a positive angle of attack. For forward movement, the aircraft had an engine with a pulling or pushing propeller like an ordinary airplane. In the incoming airflow, the rotor was able to maintain autorotation even during a vertical descent of the aircraft. The helicopter designer Pescara had patented a self-rotating rotor a few years earlier, but with a negative blade angle. Like a conventional windmill, the uniqueness of La Cierva's discovery was that a rotor with a positive blade pitch of several degrees, once spun up, continued to rotate in the incoming airflow during forward movement and generated lift. The airflow forced the rotor to rotate, but unlike a windmill, the rotor turned in the opposite direction. La Cierva discovered the effect of autorotation when he was 25 years old. He immediately patented this discovery and put maximum effort into applying this effect in practice. La Cierva initially called the system of self-rotating wings Autogyro. Auto meaning self, gyro meaning rotation. Later, he shortened the word to Autogyro because it seemed to him too Greek, too long, and too heavy. The word autogyro came to us from the French language. After deciding to apply the principle of autorotation to an aircraft, Cierva, like all his predecessors who had attempted to build a helicopter, faced the problems of rotor asymmetry and horizontal flight. It is known that the blade moving forward into the airflow at the same angle of attack generates more lift than the blade moving backward. This creates a rolling moment toward the retreating blade. To eliminate the asymmetry, Cierva chose the common scheme of that time, two coaxial rotors rotating in opposite directions. On the 1st of July 1920, Cierva filed a patent application titled A New Aviation Apparatus. The patent was issued on the 27th of August of the same year. It described the fundamental principles of a freely rotating rotor that produces lift. Interestingly, the draft of this patent contained the word Autogyro, but it was removed from the final version. After several successful Autogyro flights, Cierva asked to officially register this very word, Autogyro. To distinguish rotor wing aircraft from all others, the certificate was issued on the 7th of November 1923. For his first Autogyro, designated C1, they used the fuselage of an old monoplane, Deperducin. Cierva found it at the Civil Pilot School in Getafe. They installed a rotary Rhone engine with a power of 60 horsepower. The wings were removed, and above the fuselage they mounted two four-bladed rotors with rigid blade attachment to the hub. The diameter of each rotor was about 20 feet. The upper rotor was supposed to rotate clockwise when viewed from above, and the lower one in the opposite direction. Instead of ailerons, a vertical surface above the rotors was used, which could be turned left and right. During forward movement, it generated a rolling moment around the longitudinal axis. The tail section remained unchanged. The weight of the aircraft was about 770 pounds. The C-1 was ready for testing in October 1920. The aircraft looked so unusual that only a true fanatic of the sky, someone who dreamed of flying absolutely anything, or a relative trying to save the family's honor from ridicule, could sit behind its controls. Captain Felipe Gomez Acebo was both. He was Juan's brother-in-law, and only a few days before the trials, he had received the rank of primary training pilot. And in the future, Cierva, fanatic of rotorcraft aviation, would be fortunate to work with such devoted people. The tests were carried out at the Getafe airfield in Madrid. The flickering blades of the spinning rotors created the impression of a street fight, which is why jokers at the airfield called the aircraft La Bronca, the brawl. After the initial spin-up of the rotor, Gomez Acebo rolled across the field and began the takeoff run. Both rotors entered auto-rotation in the expected directions, but the lower one spun much more slowly than the upper one. The inventor anticipated this effect, but he had not expected the lower rotor's speed to be nearly 1/3 below the calculated value. As a result, the total lift on the left side of the rotors was greater than on the right, creating a tendency to tip over. Because of an engine failure, only a single test was conducted, but it was enough to draw at least two conclusions. First, auto-rotation was a reality. Second, compensating for the shift of the aerodynamic resultant required a new solution. Of course, Cierva could have achieved equal rotor speeds by using a gear train, but he rejected this idea, believing that such a system would become too bulky. Moreover, the cyclic variation of aerodynamic forces acting on the high-mounted upper rotor, in his opinion, would require significant reinforcement of the structure, and, as a consequence, an increase in its weight. This led him to conclude that it would be more reasonable to use a single rotor. Using the experience he had gained, Juan Cierva, with his characteristic firm consistency, set out to solve the problem of creating a rotor with a centered aerodynamic resultant, which he called a compensated rotor. To obtain such a resultant, the blade moving backward through the airflow needed to operate with a greater angle of attack than the blade moving forward. Since the lift of each section of a blade depends directly on the square of the incoming airflow speed and on the angle of attack, Cierva believed that these two factors could be combined in such a way that the aerodynamic resultant would lie approximately along the rotor's axis. In other words, the theory of the compensated rotor was based on precisely maintaining the calculated distribution of the angle of attack along the length of the blade. To make the rotor more efficient, the inventor conducted meticulous research. He wanted to find the ideal blade shape, its airfoil profile, and the angles of twist in different sections. The result was a blade with a symmetrical profile and a strong negative twist. The angle of the blades could be controlled directly from the cockpit, decreasing the angle of the blade moving against the wind and increasing the angle of the blade moving with the wind. With such a blade, which was meant to twist in flight by means of cables, de la Cierva hoped to obtain a rotor whose lift would always remain within the central plane of the aircraft. Moreover, this system allowed the pilot to control the aircraft laterally. The idea of twisting blades or wings was not new. Early monoplanes, such as the Blériot, had no ailerons, and lateral control was achieved through cable-operated wing warping, which allowed the angles of attack to change. To reduce the angle of attack, the leading edge of the wing tip was lowered, and to increase it, the trailing edge was raised. To build the Autogyro, a manufacturing base was necessary. On the 18th of November 1920, Juan de la Cierva, his brother Ricardo, and carpenter Pablo Diaz signed a contract, creating a company with a woodworking workshop for the production of automobiles, aeroplanes, and spare parts. Soon the company began constructing the second model of the Autogyro. Following the advice of his friends, de la Cierva decided to make his invention public. On the 5th of March 1921, he sent a message to the Royal Academy of Exact Sciences, Physics, and Natural History, as well as to the Royal Aero Club, in which he outlined the basic principles of the Autogyro and the results of testing the first model. At the same time, he reported that he was building a new aircraft with only one rotor. His message to the Royal Aero Club was published in the journal Heraldo Deportivo on the 5th of April 1921, and in the official bulletin of the Royal Aero Club in the same month. In March 1921, de la Cierva built a flying model of the Autogyro and tested it. The model had a 5-bladed rotor, and the tractor propeller was driven by a rubber motor. To demonstrate the Autogyro model, de la Cierva invited representatives of the Royal Academy of Sciences and members of the Technical Commission of the Royal Aero Club. Among them was the head of the Aerodynamic Laboratory at Cuatro Vientos, the FAI Sports Commissioner Emilio Herrera, the man who would later register the first achievements of the new aircraft. In the presence of the distinguished guests, de la Cierva wound the rubber band to spin the tractor propeller, spun the rotor of the model in the required direction, and placed it on the ground. As soon as he released the propeller, the Autogyro accelerated and took off, gaining an altitude of several dozens of feet, and then, as its speed decreased, began to slowly descend, demonstrating stable flight. It was clear that the loss of speed resulted in only a minimal loss of altitude. The blades continued to rotate, and the model did not fall but gently descended. The model covered a distance of several hundreds of feet, and its flight made a strong impression on those present. Everyone agreed that the Autogyro would enter practical use earlier than the helicopter. When Herrera was asked to comment on the flight, he replied that earlier he believed the first fatal crash would happen with Pesquera's helicopter, but now he was certain it would happen with the Autogyro. In this unusual manner, one of the most authoritative aviation engineers in Spain expressed the opinion that the Autogyro would take its place in practical aviation sooner than the helicopter. In one respect, Herrera was mistaken. The Autogyro proved so reliable that during 10 years of predominantly experimental flights, there was not a single fatal accident. On the 28th of March, 1921, de la Cierva filed an application for an addition to his patent. This application covered 3 of his inventions. To spin up the rotor of the Autogyro at the beginning of the run, the inventor devised an interesting method. A cord was wound around the rotor shaft, and one end was fixed to the ground. When the machine moved forward, the cord unwound and spun the rotor. Horizontal control was achieved in an unusual way, through differential deflection of the 2 halves of the elevator. These halves could work together as a conventional elevator or separately to control the tilt. The patent application included Autogyro drawings in 3 projections. The additional certificate was issued on the 20th of April 1921. Construction progressed slowly. The inventor simply lacked the funds to speed up the work. Moreover, the duralumin for the blade spars, ordered in France, was still not delivered. De la Cierva could not wait. He was eager to test his theory of the compensated rotor. Therefore, he decided to first build another aircraft, simpler, and quicker to manufacture. Thus appeared the third Autogyro, intended to test the idea of the compensated rotor and the original horizontal control layout. Although it was started later, it was completed earlier than the second Autogyro. Therefore, in the chronology of test flights, it became the second, while the one laid down earlier turned out to be the third. In books, these two Autogyros are sometimes confused. On the third Autogyro, they installed a 3-bladed rotor with a simple device for twisting the blades directly in flight. Each blade had a symmetrical aerofoil and was built like an ordinary airplane wing with a single main spar. Unlike the previous and all subsequent machines, this Autogyro had broad blades, which made it easier to tilt them. The fuselage was taken from a summer monoplane. At first they fitted a Gnome engine rated at 50 horsepower, and later replaced it with a Roan of 80 horsepower. The trials began in June 1921. The test pilot was Jose Rodriguez. Not long before that, he had received his pilot's license and naturally was eager to get into the sky. During the tests, as the Autogyro accelerated along the ground, the rotor picked up speed, but when the machine reached takeoff speed, it would hop and drop to the right. Every attempt to take off ended in damage, so the testing proceeded with long pauses. The final tests were carried out by Alejandro Gomez Spencer, who would later make the first full flight on an Autogyro, and he obtained the same result. During the ground run, as soon as the wheels left the ground, the aircraft rolled over to the right. Despite these failures, de la Cierva steadily continued his work. In all, he modified the third Autogyro 9 times. Eventually, the designer concluded that the cause of the problems with rotor compensation was the insufficient stiffness of the blades that was needed for lateral control. Because of the elasticity of the blades, aerodynamic forces caused undesirable twisting. By the end of 1921, de la Cierva had already become absorbed by a new idea that he believed would avoid lift asymmetry. The second Autogyro was almost ready, and tests of the third were stopped. The rotor of the second Autogyro, with a diameter of 37 feet 9 inches, was 5-bladed. Each blade had 2 spars, wooden ribs, and was covered with fabric. To keep the pitch angle constant, the blades were rigidly braced with tie wires. De la Cierva hoped with their help to make the rotor's lift pass through its axis. The fuselage of the second Autogyro, unlike that of the first and third, was built specially for this aircraft. The tail unit had a special feature. Both halves of the elevator could work together as a conventional elevator or separately as surfaces for lateral control. This control system in the inventor's plan was supposed to create a powerful rolling moment, so the fuselage truss was designed accordingly and provided with the proper transmission of that moment. A Roan engine rated at 110 horsepower was installed on the second Autogyro. The second Autogyro model was built at the beginning of 1922. Gomez Spencer again served as the test pilot, but despite all the new improvements, the second model behaved exactly like the previous one. The rotor spun up during the takeoff run, producing enough lift for small hops. But as soon as the wheels left the ground and the aircraft lost its firm support, it unfailingly rolled over to the right, and the lateral controls could not prevent it. Attempts to lift the Autogyro into the air ended in broken blades and a distorted fuselage because of the enormous moment produced by the lateral control. After every attempt to take off, extensive repairs were needed. The second model was rebuilt 4 times. After carefully analyzing all the experience gained from testing the first 3 Autogyros, de la Cierva concluded that with the blades rigidly fixed to the hub, it was impossible to obtain a centered aerodynamic force from the rotor. But he continued stubbornly to seek a solution to the problem because he was absolutely convinced of the correctness of the path he had chosen. After all, the principle of the Autogyro had already been proven on a flying model. In the end, de la Cierva understood the difference between real aircraft and the model. The blades of the model were more flexible. A flexible blade deforms according to the lifting force and performs a cyclic flapping motion during the rotation of the rotor. When the Autogyro moves forward, the blade advancing into the airflow rises upward, while the blade retreating backward moves downward. Thanks to the flexibility of the blade, the overturning moment transmitted to the rotor axis becomes insignificant. Thus, the reason for the different behavior of the model and the real Autogyro was determined. Now it was necessary to build a rotor in which the blades could perform flapping movements. And de la Cierva decided to attach each blade to the hub using a hinge with a horizontal axis. For now, only a single hinge, In 1927, he would add a second one with a vertical axis. About the moment when this idea first occurred to him, de la Cierva wrote the following. In my notebook, where I recorded calculations for several years, I found an entry stating, on the 2nd of January 1922, the idea of hinging the blades occurred to me for the first time. Clearly, at first this decision was only an alternative option for the designer. Only after testing the second model did he finally become convinced of the necessity of using a hinged rotor. On the 18th of April 1922, de la Cierva filed a patent application for a hinged connection providing the flapping movement of blades in the vertical plane. The patent, Improvements in Aeroplanes with Rotating Wings, was issued on the 15th of November of the same year. Now, the hinged connection allowed the blades, during rotation, to form a cone determined by the balance of aerodynamic and centrifugal forces. The flapping motion was damped aerodynamically. A blade rising upward automatically reduced its angle of attack and, accordingly, its lifting force. This caused it to reduce the speed of its flapping motion and then descend. Conversely, when the blade descended, its angle of attack increased. On the first autogyros with horizontal hinges, de la Cierva used rubber cords for blade suspension. Even with the rotor stopped, they held the blade almost horizontally. During motion, the centrifugal force is approximately 10 times greater than the lifting force, and the blades do not need suspension. Suspension becomes necessary when the rotor is at rest or at low revolutions, when the lifting force is still insufficient. The patent also contained another point. The spar of the blade near the root section was bent downward, so the hinges were positioned below the blade's center of gravity. The designer believed that during flight, the blades would take an almost horizontal position. This spar shape was used only on the fourth model, which will be discussed below. Juan de la Cierva believed that introducing the hinged rotor provided 6 key advantages: a centered aerodynamic resultant force, improved stability in the air because the lifting force always acted above the aircraft's center of gravity, the ability to use superior blade airfoils that previously could not be applied, the elimination of loads that bent the rotor axis, the absence of the gyroscopic effect that interfered with control, and the overall simplicity and lightness of the entire structure, which together ensured the first successful flights of the Autogyro. The first Autogyro with hinged blades had another innovation. The pilot could tilt the rotor axis to the left and to the right at will. Previously, roll control was achieved using a single aileron above the rotors or a special mechanism for twisting the blades or a differential elevator. Now they attempted to control roll using the rotor itself. For building the new machine, de la Cierva took the fuselage of the previous model but significantly modified it. He installed a Rotor engine with a power of 80 horsepower. The Autogyro used a 4-bladed rotor. Each blade had a single tubular spar and wooden ribs. The trials began in June 1922. At first, the taxiing and ground runs were performed by Gomez Spencer, but he was soon recalled to the Army, and the tests were continued by Jose Maria Espinosa. The trials again did not produce the expected result. The pilot could not tilt the rotor axis. It required superhuman strength. They had to return to a conventional airplane control layout. La Cierva understood that this was a step backward, but at that moment it was necessary above all to prove that the Autogyro principle worked in practice, and only then improve the controls. The rotor control was removed and instead a transverse beam with ailerons was installed. By that time, Gomez Spencer had returned and continued the trials. In January 1923, the first successful flights finally took place. Different sources give different dates for the first flights, so for accuracy we will quote an excerpt from La Cierva's report to the Royal Academy dated the 15th of February 1928. This aircraft, tested in June 1922, demonstrated from the very beginning its inherent automatic centering and was already ready to fly. But a failure occurred that forced the trials to stop. Due to the absence of a pilot and for other reasons, they could not be resumed until January of the current year. The aircraft is now equipped with 2 small ailerons, that is, small wings for lateral control. Piloted by Mr. Gomez Spencer, the Autogyro took off for the first time on the 10th. After compensating for the reactive torque of the engine, on the 17th it made several straight-line flights at an altitude of 6.5 feet, confirming all the calculated data except for the landing, which was carried out in an airplane-like manner. On the 20th, due to a defect in the engine control system that prevented the pilot from shutting it off during landing, the aircraft climbed to an altitude of 26 feet, which, with a loss of speed, would have threatened catastrophe had it been a conventional airplane. The pilot, remembering the theoretical property of the aircraft to be insensitive to loss of speed and its ability to land vertically, performed the necessary maneuver. The aircraft slowly descended and touched down almost without forward speed, fully confirming all of its theoretical characteristics. On the 25th, official tests were conducted, and on the 31st, a flight lasting 3.5 minutes was made along a closed course 2.5 miles long at an altitude of more than 82 feet, as confirmed by the certificate, a copy of which I am attaching. Thus, on the 10th of January 1923, Gomez Spencer took off for the first time in the new Autogyro. The hop was brief. The Autogyro banked to the left and fell. The cause was the reactive torque from the tractor propeller. It was eliminated by shifting the rotor axis to the side. And on the 17th of January, Gomez Spencer made the first straight-line flight at an altitude of 6.5 feet with a distance of 600 feet. Thus, the hinged rotor allowed the Autogyro to fly. On the 20th of January, during a low-altitude flight, the engine suddenly malfunctioned and went to maximum RPM. The Autogyro began to climb rapidly, but the pilot managed to switch off the ignition, pulled the control stick sharply toward himself, and the aircraft landed with a small vertical speed. This flight was described by the head of the Getafe airfield, Captain José González, as follows. During the test performed by Lieutenant Alejandro Gomez Spencer on the flying machine invented by the road engineer Juan de la Cierva and named Autogyro by the inventor, due to a malfunction in the manual contact circuit, the aircraft suddenly rose to approximately 26 feet, and at that altitude found itself without forward speed, that is, in a situation corresponding to complete loss of speed for an airplane. However, during the descent, lift was continuously present thanks to the rapid rotation of the wing blades, which resulted in a soft, smooth landing. Without doubt, González described this incident at La Cierva's request. The inventor needed confirmation from an official authority about the main advantage of the Autogyro over the airplane. An airplane survives only through speed. Without speed, it cannot remain in the air. At the dawn of aviation, airplane speeds were comparable to the movement of air masses, and in some cases, when the pilot's experience was not taken into account, conditions could arise in which the wing reached beyond critical angles of attack, leading to an abrupt stall into a spin. Losing speed at high altitude is not as dangerous. When entering a spin, the aircraft can be recovered, and once it regains speed, it can return to normal flight. But at low altitude, the chances of saving the machine, and often one's life, were almost non-existent. That is why La Cierva wanted to emphasize the advantages of his new aircraft, which found itself in such a critical situation. After these flights, the aircraft was transported from Getafe to the Cuatro Vientos airfield, where a military aviation base was located. It was there that on the 31st of January 1923, Gomez Spencer opened the era of normal rotorcraft flight. The sports commissioner of the International Aeronautical Federation, Herrera, certified this flight in an official document. At the Cuatro Vientos airfield in the afternoon of the 31st of January of this year, the aircraft of the Autogyro system, invented and built by Don Juan de la Cierva Codorniu, piloted by Lieutenant Alejandro Gomez Spencer, carried out 3 flights, the last of which was performed along a closed route approximately 2.5 miles long over a period of 3 minutes 30 seconds, reaching an altitude above ground of more than 82 feet. With this historic flight, the effectiveness of the Autogyro principle was proven in practice. The aircraft had fulfilled its purpose, and for more complex experiments, a new machine needed to be built. The successful Autogyro flight received wide attention in the world press. The American magazine Aviation, already on the 12th of March, placed a photograph of the Autogyro on its cover, and on the 9th of April published an article about it by the pioneer of Spanish aviation, Heraclio Alfaro. The French magazine Aéronautique, in its April issue, printed a short article by La Cierva that listed the following characteristics of the aircraft: rotor diameter, 26 feet, total blade area, 108 square feet, blade airfoil. Eiffel 101, engine, RON, 80 horsepower, takeoff weight, 1,100 pounds, specific blade loading, 10.2 pounds per square foot, maximum speed, 62 miles per hour. Of course, the maximum speed was never measured properly. This figure was certainly an estimate and most likely an optimistic one. In the above-mentioned report to the Royal Academy of Sciences dated the 15th of February 1923, Cierva writes after describing the flight of the 31st of January 1923, "With this experiment, I conclude the work on the current aircraft, which is not prepared for long-duration or long-distance flights, and I shall begin creating another aircraft of the same characteristics but of improved design, the construction of which I hope to finish quickly. The purely experimental part is complete, but this does not rule out possible future improvements, especially in the field of useful efficiency. Conclusions. I have the honor to report to our Royal Academy of Sciences that the result of my research into the Autogyro system has been the creation of a flying machine with the same characteristics as an airplane, but with advantages in stability and landing, ease of construction, and simplicity of control. At the same time, the Autogyro approaches the airplane in useful load and speed. Thus, one historical stage has come to an end. The inventor now begins working on the further development of the idea. After the successful flights of the fourth Autogyro, Cierva began building his fifth machine. Despite financial difficulties, he carried the work through to completion. It was the last Autogyro created by the inventor at his own expense. Taking into account the modifications and major repairs, he built 30 Autogyros at his own expense. The rotor of the fifth Autogyro had 3 blades. In Cierva's view, a 3-bladed rotor had less mutual interference between the blades compared to 4- and 5-bladed rotors. Each blade had a single spar of mixed construction, a plywood skin, and a metal edging along the rim. The engine on the Autogyro was a Juan with a power output of 110 horsepower. Testing began in April of 1923. Because of frequent breakdowns, the work progressed with interruptions. Eventually, the aircraft suffered a serious accident. During taxiing, a blade spar broke due to material fatigue. The machine was no longer repaired. The inventor's resources had been exhausted.